Good afternoon, everyone. My name is Peter Scott. I'm a graduate student in the Reacting Gas Dynamics Laboratory at MIT. And today I'll be presenting on work that we've done to design and model an indirectly irradiated solar thermochemical hydrogen reactor for use in a reactor train system. So just to give some background and motivation, the stuff I'll be talking about today is based on the same process that Waymo just described, the two-step thermochemical water splitting reaction using a metal oxide, in which a metal oxide is cycled by bringing it to extremely high temperatures and low partial pressures, around 13 to 1500 degrees Celsius, and then to reduce, and then is brought down to a much lower temperature at atmospheric partial pressures, around 700 to 1000 degrees Celsius, where it is reoxidized with H2O, and the oxygen goes, sorry about that, the oxygen goes back into the lattice of the metal oxide, and the hydrogen is left behind as your product. And in order to attain these extremely high temperatures, current demonstrated systems have used concentrated sunlight, such as what Waymo just presented, and also heliostat fields. So in general, the reason that our field is looking at heat instead of electricity for hydrogen production is because heat can be harvested from the entire solar spectrum, as opposed to a thin region of the solar spectrum for electrical purposes. And this leads to high theoretical efficiencies. And storage of heat is also potentially cheaper and could enable higher capacities for a hydrogen system. However, as Waymo also started to get into, there is a key issue of heat recovery when we're looking at getting higher efficiencies in the system, because there is a huge discrepancy between the upper and lower temperatures in this system. And if you're not recovering that heat when you bring the metal oxide back down to the oxidation temperature, you're losing just a massive amount of it, which is all sensible heat and not going into the reduction reaction. So in order to address this issue of heat recovery, a few years ago, people in our lab came up with a concept called the reactor train system. And you can see an animation of it up here. In essence, the way that it works is these boxes all represent individual thermochemical reactors, which each contain a bit of redox material, metal oxide, and they're cycling continuously between a high temperature reduction zone and a lower temperature oxidation zone. And the key innovation here is that in between these two steps, they are engaging in counterflow radiative heat exchange, which could potentially lead to very high heat exchange efficiencies. Another key difference between the reactor train system concept and existing demonstrated systems is that it would be heated by a diffuse emitter that is connected to a thermal energy storage. Now, this would enable heat from a wide variety of inputs, such as concentrated solar or even excess renewable electricity. And a system like this has never been built before, and it will obviously require a novel reactor to be built specifically for it. And that's where my research comes in. This reactor needs to be designed not to trap sunlight, but instead to efficiently transfer infrared radiation. So to get a bit more into that, let's look at what a directly irradiated reactor typically looks like. It uses concentrated high flux solar spectrum radiation to heat it, and it is not designed for radiative heat recovery, which means anything coming back out of the reactor is just lost to the environment. Therefore, it is designed to trap sunlight by using a cavity geometry and a small aperture, which is typically actively cooled quartz window. On the other hand, this is what an indirectly irradiated reactor could look like. It uses diffuse lower flux infrared spectrum heat from a diffuse emitter, and it is designed for radiative heat recovery So any re-radiation coming back off the reactor would stay in the system because it's reabsorbed into the emitter or an opposing reactor. Because of these differences, it has a more flexible geometry. It doesn't need to have this cavity geometry, and it will need a larger heat transfer interface because we're using less concentrated radiation. And a larger interface is better for the speed of heat transfer. So this is what our reactor concept currently looks like. This is not finalized, but this is what we're currently thinking of it as. It features a uncooled absorber emitter structural vessel that is made entirely out of sintered silicon carbide. The reason we chose this as our material is because it is high strength, thermal shock resistant, and oxidation resistant. Around the entire reactor, we would have lightweight ceramic insulation to prevent heat losses, and we would also have this insulation separating the hot redox zone from the cooler zone down here, which would be serviced by high temperature metal alloy components, which cannot withstand the full temperatures of the redox phase. So the advantages of such a system are that it is an uncooled design. We previously looked at reactor designs that involve a infrared transmitting window, but our preliminary modeling showed that this requires some level of active cooling in the system and very high heat losses due to the properties of infrared transmissive materials. So this design does not use any of that, and it would result in reduced losses and also engineering simplicity, because we're using this would eventually be a moving reactor, and that would be very hard to have an active cooling system in it. It's also expandable and modular. You can stack these silicon carbide vessels next to each other in order to obtain a larger reactor. Now, the challenges of using a system like this are that we're using opaque silicon carbide, which means we're going to have slower heat transfer to and from the redox material because it needs to heat up to re-emit. Since we're also going to have a high temperature structural component, this means we'll need to use more heat to get it up to temperature. And it will also experience significant thermomechanical stresses, which will need to be seriously considered. I'll show that in the next few slides. So this is what the reactor would look like in a 8-reactor RTS, cycling between the hot emitter and the heat sink side, and it's always facing each other. So to model the heat transfer and mechanics of the system, we created a finite element model of it in console multiphysics. And the dimensions you see here are not finalized or optimized, but this is an example that we will be using to show some sample results. So in order to stimulate a thermal cycle, we impose a diffuse emitting boundary condition with a temperature profile, a sample temperature profile that goes from 700 to 1600 degrees Celsius, some slight underheat and overheat. This is not meant to perfectly simulate what the reactor would experience in a reactor train system, but it is meant to provide a baseline thermal cycle to see how the reactor responds to thermal cycling and compare different reactors' designs. It uses high fidelity heat transfer physics with surface to surface radiative heat transfer and assumes that the redox material is that same porous ceria that Remo was talking about before. We model this using the P1 approximation. We take some simplifying assumptions in our modeling. We're assuming that ceria is always in thermodynamic equilibrium with 200 Pascal oxygen partial pressure throughout the entire cycle. So this means that the oxidation phase is not going to be completely resolved. And we also don't include a gas-based physics. So we're assuming that radiation is the dominant form of heat transfer. The top face of the insulation is also assumed to be adiabatic because it's always going to be facing another reactor. So here's some sample heat transfer results. We can see in this animation showing the temperature fields throughout the entire cycle that the redox zone is undergoing a significant temperature swing, while the inner insulation is successfully shielding the metal components at the back of the reactor from this high temperature swing and keeping it at a lower, more acceptable temperature that could be used for something like Inconel. We also have here a plot of the time-dependent average Syria temperature in solid black and maximum Syria temperature in dash black lines. And while we can see that while this design using the opaque absorber emitter does result in some temperature dampening response, it doesn't reach the full temperatures of the emitter, we are attaining viable redox temperatures. And we can also analyze the energy flows in the first 30 minutes, which is the heat up and high temperature phases, to see where the energy is going. And we can see that about half of it is going into sensible heat of the structural and non-redox components. About a quarter of it is going into the sensible heat of the redox component. And the rest of it is either lost through the sides or is going into the reduction reaction. What our heat transfer model also enables is thermal expansion analysis, which I will get into next. So for our mechanical modeling, we take a pretty simple approach of just using a linear elastic model that accounts for both thermal expansion and mechanical forces. In the example that I'm going to show, we're assuming just the silicon carbide vessel is modeled. It's under constant vacuum and it's minimally constrained. What we then do is we take our stress data and we put it into a fast fracture failure probability model, because we're using a ceramic here, and ceramics don't necessarily fracture at one given stress value. Instead, ceramics really fracture due to random flaws distributed throughout the material, and it's dependent on the size of the component as well. So to model this, I use something called the Shetty's mixed mode criteria model, which is a crack shape dependent model. It basically calculates the probability of failure for each finite element and then combines them all, assuming that if one finite element fails, the entire component will fail because of the weakest link theory approximation for structural ceramics. We use the stress field at the time of maximum tensile stress because ceramics are weaker in tension than they are in compression. So here's some sample mechanical results. We can see here the stress field, the tensile stress field over an entire cycle, and in this inlet is the area where the maximum tensile stress occurs on the outside, 68 megapascals. This spatial data is very important for our modeling, as it shows where we need to focus on to improve mechanical stability. In this plot, we can see in red the silicon carbide maximum tensile stress, and in magenta, the silicon carbide maximum temperature gradient. And what we see is a very strong correlation between the two at their peak. So this temporal data can also show us when the maximums are occurring and what we need to focus on if we want to reduce stresses. And when we plug the maximum stress field into our failure probability model, it gives us, gives us a number which is 1 in 6,400 for this specific case. For this specific case, we can see so the model is by no means a definitive model, but it's very helpful for us in turning a value for tensile stress that might be somewhat nebulous into a more tangible number for our design purposes. So these models are enabling us to study many parameters, including geometry, cycle temperatures, cycle times, and material properties. So to exemplify how we're using these modeling capabilities to design a better reactor, I'll show one example of a parametric study where we vary the silicon carbide thickness from the 5 millimeters we saw before to a 7.5 and a 10 millimeter variant. So what we can see in this plot is the Syria average temperature in solid black for the 5 millimeter, dashes for the 7.5, and dots for the 10 millimeter. And what we see is that predictably, when we go to thicker silicon carbide, we have a greater temperature dampening response. But what our models allow us to do is really quantify that, and what we can see is that we can see the exact difference in the maximum average Syria temperature that is attained. While this might not seem like a lot, this is actually going to end up being a lot in terms of reduction extent at these temperatures. We can also see that the thicker silicon carbide results in higher temperatures at the base plate joint because it's conducting more heat down to the base plate, which is not desirable. And it also uses more energy input to heat that big hunk of silicon carbide. As for our mechanical results, we can see that when we go thicker, we actually end up increasing the maximum tensile stress and the failure probability. And interestingly, the position also changes to a different spot. So while this is while this might seem a little bit surprising at first, it can be attributed to the fact that the stresses here are dominated by thermal expansion. So making a component thicker will not always help you in terms of mechanical stress. So in summary, we conceptualized an indirectly irradiated thermochemical hydrogen reactor to be used in our group's novel reactor training system. We developed detailed thermal and mechanical modeling capabilities for design purposes. And in our ongoing and future work, we're going to build upon the model by adding gas phase physics, detailed oxidation phase modeling, and more. And we're eventually going to use this model to converge on an optimized prototype design, which will then be constructed and tested. So thanks so much to the conference and session organizers and my team. And I'll be taking questions.
Thank you. About 3 minutes for questions. Who'd like to go first? I'll start with getting into the efficiency. So what I took away from the previous talk was that efficiency of the whole system will depend on like several factors going together from the parts of the system. Do you have that to show? Like, does this go with the previous talk in terms of like trying to improve its efficiency, or is clearly this train is giving you a lot big efficiency boost? Does it fit into the overall system and make a big impact?
Yes, so that's a great question. And yeah, I don't have a lot of efficiency numbers up in this presentation. The reason for that is because my work is currently focusing on just the reactor design and modeling portion of it. And it will take more, it takes more than just that part of the system to estimate efficiency, since there's also pumping, there's pumping and auxiliary energy savings and inputs. So while that's not a part of my work, we do have other people in our lab who are working on efficiency estimates for the system. While I'm not going to give any specific numbers, what we are pretty confident in is that our system should be able to attain higher than what the current demonstrated best is, which Ramos said before, 5.6%. Yeah, we're looking at least heat recovery numbers that could be above 50% heat recovery, which should hopefully result in higher overall efficiencies. Yeah.
Great, definitely. Thank you. Question up there.
I don't know if you mentioned it. What insulating material are you using? Why did you choose that one?
Good question. We don't have a specific insulating material in mind yet, but what is most likely would be alumina. There's a lot of lightweight alumina ceramic insulations out there in both solid and kind of like flexible forms that we can use. That's what most of these systems use for their insulation.
Which one did you model in like that graphic?
Say that one more time. Sorry.
Like you had a graphic that actually showed like the temperature distributions going through the insulating material. Which one did you use for that?
Alumina. Yeah, we're using alumina properties, texture properties for, yeah, for this right here.
Okay,
Yeah.
thank you.
Of course.
Great, thank you for the question. We'll move on in the interest of time. Let's thank our speaker again.